Hello everyone. So we have a good question from the chapter of rotational motion. So let's just have a look at the question once. So this is a uniform bar and its length is 6a, mass is 8m, and it lies on a horizontal table. Okay, so this is all happening on a horizontal plane, and a mass of 2m and a mass of m are attacking this particular bar from opposite sides with velocities v and 2v respectively. Okay, and we have to find number one, we have to find the velocity of center of mass of the system, and number two, we have to find angular velocity of the rod about the center of mass of the system. Okay, so yeah, let's begin. So let's try and calculate the uh, center of mass velocity, right? That's what we want. Yeah, center of mass velocity of this particular question. So let me just draw the bar once. So this is the bar with a center at O, and at a distance 2a here, a mass is a mass of m, a mass m with velocity 2v is approaching this, and at a distance a over here, a mass 2m is coming. Okay, so we will simply apply law of conservation of momentum, law of conservation of momentum. Okay, we will apply this, and since momentum is a vector, let's just define which side is positive. Let this side be positive and this side be negative. Okay, so this particular body is moving from positive to negative, right? So the sign of this will be negative. So this is moving with a velocity of v, right? So uh, the initial momentum is 2mv, and this body here, it's moving from negative to positive. So the momentum will be positive, right? So this will be 2mv, and the final velocity will be uh, the total mass of the system. That is, this is 8m, I suppose. Yeah, this is 8m plus 3m. Okay, so 11m into v center of mass. Now, very obviously, the value of center of mass will be 0. Okay, so we have our first answer. Okay, there it is. Now, we have been asked to find the angular velocity of the rod about the center of mass of system. So what will be the center of mass? So once these two bodies come and attach over here, okay, these two bodies will come and attach over here, right? This is at a distance 2a, this is at a distance a. Okay, now um, just a second. So this is 2m. I mean, just by looking at it, you can see that the lighter mass is at a distance of 2a away from the center, right? And the heavier distance, I'm sorry, the heavier mass is at a distance of a. So essentially, when we are finding out the center of mass, this is how we find center of mass, right? Summation x1 m1 divided by summation m1, right? This is how we find the center of mass, because you see, when we okay, so suppose, let's consider this side to be positive and the other side to be negative. So this is what it will look like, right? um, and O is the origin, so this will basically be mass m, the x is 2a, and this is minus 2m into a, plus the mass of the rod into 0, right? Divided by the summation of m. This will essentially be 0, right? Because these two are getting cancelled. So the center of mass is basically O. O is the center of mass. That is the center of this bar of mass 8m. So what we will do is we will basically conserve the angular momentum about the center of that rod. Okay. So applying law of conservation of angular momentum about the center, about O. Let's just write O. Okay. So this will be, you see, 2v into m into a, into 2a, I'm sorry, to 2a plus 2m into v into a. This will be equal to I omega, right? This will be equal to I omega. Okay, in case you did not understand what I did here, see, um, basically the formula is for angular momentum is r cross mv, right? R cross mv. And what matters here is r cross v because m will move outside anyways. It's a constant, right? So if you see, when you perform this particular operation of r cross v, you will find that both, suppose the first one, this is r and v is this, right? This is r and this is v initially. So when you perform cross product r cross v, you will find that that vector is coming upwards. Okay. And when you are doing the same for the body on the left, when you're doing the same for the body on the left, this will essentially be, this is r, this is v, right? So r cross v is again, the vector is upwards. So if we consider uh, the top to be positive, and so they have the same sign, right? Unlike this momentum conservation where the sign will become different for bodies coming from opposite sides, uh, the angular momentum will have the same sign for the reasons which I have mentioned. So this will be I omega. Okay, so let's calculate the I. So about the center of mass, the moment of inertia of a rod, it is ml square by 12, right? Now the mass of the bar is 8m. So it will basically be 8 ml square by 12, right? Now we have got the two bodies of mass m and 2m which are attached. So one body will have 2ma square as the moment of inertia, right? Because 2m is at a distance of a, and another body will have m into 2a square, which is 4ma square. Okay. This multiplied by omega, this will be the angular velocity about the center of mass of the body. Now, what is the distance L? L is 3a basically, right? Where am I? Okay. L is 3a. So this will be 8m by 12 into 36 a square, right? Because L is the total length, which is not 3a, I'm sorry, it's 6a. So this is what it will turn out to be. Let's now cancel this 12. Okay. And so the sum will be 24 plus 6, that is 30. Okay, it is 30 ma square, which is equal to 30 ma square omega. And on the left hand side, we have got 4 and 2, 6 MVA. 6 MVA is equal to 30 ma square omega. So let's just cancel everything from here. The mass will be cancelled, A will be cancelled, and 6 and this will be 5 will be remaining. Okay. So the answer of omega will be equal to V by 5A. Okay, that's the answer. So yeah, please be careful when you are computing, when you are, trying to get the sign for angular momentum and momentum as well. It can sometimes be tricky. That's it from this video. Thank you.